acute trauma immediately damages the spinal cord. This primary damage, injured neurons, glia, myelin sheaths, and blood vessels, starts a relentless cascade of molecular and cellular events. The damage caused by these pathological mechanisms is known as the secondary spinal cord injury and is responsible for most of the debilitating effects of spinal cord injuries. Secondary, unlike primary injuries, are not due to mechanical forces, but are the result of ischemia and changes in molecular composition that lead to neuronal death. The release of glutamate from damaged neurons is one such inciting mechanism. Because of damaged uptake systems, glutamate is left to accumulate in the extracellular space. At the postsynaptic membrane, glutamate continually activates AMPA receptors, which chronically depolarizes the neuron. Chronic depolarization keeps voltage-gated sodium channels open along the axon, allowing a continual influx of sodium into the neuron. This buildup of intracellular sodium has fatal results. Sodium-calcium exchangers are driven into reverse operation, triggering excessive calcium influx. Simultaneously, chloride ions enter the neuron in an attempt to balance excessive positive charge, bringing with it the dangerous accumulation of water. Water influx forces the neuron to swell. These catastrophic changes in cell volume and metabolic state degenerate previously intact functional neurons. The damage done by excess glutamate is not limited to neurons. Diffusion of glutamate into the extracellular space also adversely affects surrounding oligodendrocytes. Glutamate binds NMDA and kainate receptors on oligodendrocytes. Once activated, sodium and calcium pour through these receptors, depolarizing the membrane. Chronic depolarization perpetually opens voltage-gated calcium channels so that even more calcium spills into the cell. Excess intracellular calcium quickly results in apoptosis. Without oligodendrocytes, denuded axons will not be remyelinated. This impedes neuron function. Microglia and macrophages phagocytose the resulting cellular debris, leaving an open space. Macrophages attract astrocytes, which enclose the empty space to form a glial scar. Astrocytes also secrete CSPGs, which disrupt neuron growth. On the surface of growth cones, CSPGs, inhibitory guidance cues, and myelin-associated inhibitory molecules activate a signal transduction cascade. Once phosphorylated, myosin contracts to pull the actin cytoskeleton inwards. Growth cones then collapse in on themselves, eliminating any chance of axon elongation and spinal cord repair. In addition, macrophages directly attack growing neurons, forcing them to retreat backwards. New growth through the site of injury is therefore stopped at the glial scar. All these pathological mechanisms combine to form the secondary spinal cord injury. With further intensive research, these mechanisms may be better understood and their effects attenuated so that the devastating outcome of spinal cord injury can be reduced and perhaps ultimately avoided altogether.